this now? Okay, so we're very happy to have Jesse Thaler, who's a professor at MIT, who works on jet physics and using SCET techniques to look at LSE data, etc. And he'll talk today about the hidden geometry of particle collisions. So the floor is yours now.
Great. Thanks so much. It's a pleasure to be here remotely, and hopefully at some point I'll be able to actually visit you all in person. So today, particle collisions, and hopefully this will become clear what I'm talking about as we move ahead in the talk. Maybe just to start, we can talk about the manifest geometry that we're more familiar about talking about with particle collisions. Where we often think about the geometry of a single collision event. So for example, we would talk about isometries of collider data, symmetries or approximate symmetries like longitudinal boost invariance, or azimuthal symmetries where I rotate the detector cylinder. And there's various geometric data processing techniques that we're familiar with using. For example, things like jet clustering, or the field that I'm involved in, looking at the substructure of jets, kind of looking at the topology of collision events. So there's a huge literature about geometric strategies for studying collisions, single collisions, but that's not really what I'm going to be talking about today. What I'm going to be talking about today is an emergent geometry that comes when you're looking at many collisions. And so this is a more abstract geometry, which I'll be explaining about in this talk. And here what you're seeing is you're seeing the space of jets. So this is data, in fact, taken from CMS, a public data sample. And this is an analysis that I did with Patrick Comiskey, Eric Metodiev, Preksha Nayak, and Radha Masandria. And what this is, in gray, it's showing a distribution in the space of events. And these 25 circles represent example jets in this space. So this is not a space that many of you are familiar with. I'll be explaining more of this in this talk. But here you also have elements that are familiar from our understanding of QCD. So this is a two-dimensional projection of a space, and I'll explain what the dimension of the space is later. But roughly speaking, the dimension of the space corresponds to the opening angle of emissions and the energy sharing, the Z factor of emissions in QCD. And we'll stare at this a little bit more later in this talk, but this is the emergent geometric structures that I want to be explaining more about in this talk today. Now, I'm calling this an emergent geometry because this is something that might not have been obvious to you until you started using this geometric language that I'll be explaining about. But the title of my talk is about hidden geometry. And the reason why I call it a hidden geometry is, in fact, these ideas that I'll be talking about have been around in our field for a while. We just didn't have a name for them. And an example that I'll explain in more detail later is classic QCD event shapes. And ideas in particular, this going back to, for example, my work by my colleague Eddie Farhi in the 1970s of understanding the thrust of collision events and electron-positron collisions. And what I'll explain to you in this talk is that there's a geometric way of understanding things that we've been talking about for many decades. So for example, we have this collision event taken from the Aleph detector. This will get mapped in this geometric language that I'll explain to a single point in an abstract space. And then what we're going to understand is we're going to understand that event shapes like thrust can be thought about as the distance of closest approach to a manifold in this abstract event space. And in fact, a number of things that we're familiar with in our understanding of QCD and collider physics come from or have a manifestation as geometric quantities in this abstract space. And that's what I want to explain to you in this talk today. Just as an aside, the ideas that I'll be talking about today came about from work that I did during my sabbatical. So I had a wonderful sabbatical year, and I took my students with me on various adventures. So here's an example of me, my student Eric Metodiev, who in fact just defended his PhD thesis earlier this week, Patrick Comiskey, and we went to CERN, and we had a road trip going around Lake Geneva. So here you can see us in the CMS cavern, having coffee by the lake, This is the recording studio where Freddie Mercury and Queen recorded their last album. Here's a traffic stop where, in fact, some of the ideas that I'll be talking about today were developed. This just goes to show that sabbatical time can be very productive. And the ideas here were really surprising to me, and it was a pleasure to work with my collaborators, Eric and Patrick, to make this hidden geometry story. One final thing before I launch in, this is a remote talk. Sorry, this is a remote talk, so please interrupt me or drop questions in the chat, and I'll try to answer them as I go. So I have the chat window open on my screen. I can't see the raise hand feature, so don't use that, but just interrupt me if anything comes up or drop a question in the chat, and I can make sure to pause my discussion. Okay, so what I want to do in this talk is start very basic, just answer the question, what is a collider event, and introduce you to the language that I'll be using in this talk. And then ask a question about when are events similar. And this notion of similarity will allow us to define this emergent geometry that I pointed to. And then we're going to spend the bulk of the talk talking about what are the types of things that can be geometrized, what concepts from quantum field theory and collider physics have a geometric interpretation. Okay, so let me just pause for a second to see if there's any questions before I move on to the rest of the talk. Okay, great. Okay, so let's start off with the simple question, what is a collider event? So for this audience, I think we're all familiar what collision events look like. One way of thinking about collision events is that they are points in momentum space. So while it's true that we can use various different detectors, tracking, calorimetry, muon detectors to do particle identification, for the purposes of this talk, we're just going to imagine that what a collider event is just a set of points px, py, pz, so points in momentum space, corresponding to the particles produced in a single collision. What's kind of nice about this data structure, just a collection of points in momentum space, is that this is a data structure that other fields of science have studied a lot. And there are other domains where this notion of points in an abstract, or points in a physical space are relevant. For example, something that is, on the horizon are self-driving cars, and LiDAR detectors for self-driving cars have the same type of data structure. That is, this LiDAR detector picks up points not in momentum space, but points in position space. And a lot of the data processing techniques that are relevant for self-driving cars and machine learning for self-driving cars are relevant in the collider context. So for example, we want to find clusters of points that are linked together. Of course, we know what that means in the collider context. Clusters of points linked together, those are jets. In the self-driving car context, we'd like to do classification, tell the difference between a bicycle, a car, a pedestrian. In the jet physics context, we would like to be able to identify whether these clusters, whether they're coming from quarks or gluons or some other hadronic object. So there's interesting similarities between the data structures here and here. And I could give a whole talk about the relevance of machine learning and the intersection of this. But here I really want to just focus on the data structure. And the difference in the data structure from the collider context compared to the self-driving car context or other contexts where we have what are called point clouds is that we know a lot about our collider data, where it comes from. And in fact, a lot of the information is non-perturbative and therefore not understandable, and therefore we'd like to suppress it. So let me just review this. So in the standard picture of how jets form, we have a hard process, a collision that generates quarks and gluons in the hard scattering process. Those shower and radiate in the parton shower. We have non-perturbative hadronization. And is in the end state. We can calculate in perturbation theory most reliably, and also the thing that's most experimentally robust is just the overall flow of energy into the final state. So we can define a stress energy flow operator. The stress energy flow operator is just composed out of the stress energy tensor, so T mu nu, but we take the zero component That's the energy. The I component is just the flow of energy. And the flow of energy off to infinity, we can define that with a quantum mechanical operator, and correlations of these stress energy flow operators. That's basically the information that's robust to non-perturbative and detector effects. That is the least senseless gauge theories, talking about the number of particles is not really well defined, but talking about the flow of energy, that is something that is well defined and calculable. So we're going to be focusing on just the stress energy flow of an event. And what that means is that instead of having a generic point cloud, that is, instead of having a data structure like this, what we have is a weighted point cloud where we only study the flow of energy and we suppress charge and flavor information. So the data structure that we have is, okay, our standard four momenta, but we're going to separate this into a direction. So that's these, let's say, represented by these purple lines, and then the amount of energy that's represented by these calorimeter deposits. And we're not going to consider charge and flavor information because that's something that's not well defined for massless gauge theories. And so we're going to focus on the things that are most robust. And what we'll see in this talk is I'll show a representation of this weighted point cloud, or a representation of this energy flow as a energy density. And so if I take my detector and just take a patch of it, and this is now a head-on view of a jet, and I now represent the energy depositions in an idealized calorimeter. We have energy deposits, or in the case of hadronic calorimeters, PT deposits, localized at some point, in this case in rapidity azimuth space. And this energy density, that's going to be the answer to the question, what is a collider event? A collider event is a kind of idealized calorimeter energy density. And this perspective is kind of cool in a machine learning context, but here I'm just going to say this is the information that's non-perturbatively and detector robust, and we're going to treat collider data as just this information. So I'm suppressing flavor information, I'm suppressing charge information, and I want to ask the question, what can I learn about field theories if I focus on just this energy density information?
Just one question, Jesse.
Yes.
Every particle is massless for you in this particular setting for now.
So actually, in the appendix of our paper, my paper with Eric and Patrick, we actually talk about what happens in the massive case. But yes, for the purpose of this talk, imagine that all the particles are massless, or you make them all massless. It makes the algebra a little bit easier. But actually, this whole story goes through, even if you include particle masses. And if you want to read more about that, there's this paper that I wrote with Vicente Matteau and Ian Stewart back in 2013, where we actually generalized the stress energy flow operator to handle the massive case. And it's kind of hidden here. There's this V term here, which is talking about the velocity of particles. And if you actually track not just the flow of energy, but the speed at which that flow is going, that allows you to treat the massive case. And then there's an equivalent way of talking about this energy density. Now you can talk about not just direction and azimuth and rapidity, but also the velocity. And so that's a harder thing to show on the screen, but you can talk about energy densities in rapidity, azimuth, and velocity space. And that is the most natural way of representing massive particles. But for the purpose of this talk, let's just treat everything as massless for simplicity.
Yeah, okay.
Great. Other questions before I move on? Okay, so that's what a collider event is for the purpose of this talk. So that hopefully this is very basic for you. Now let's talk about a question that you may or may not have thought of. When are events similar? Or said another way, when are energy densities similar? So here is an example of two collider events. So now we have two collections of points in momentum space.
Sorry,
and you can
Jesse,
ask, well, how close are these to each
Jesse,
other?
can I ask a question?
Yeah, sure. Hi, Tune.
Hi. So you are, am I right in thinking that you are thinking of, for a single event, you would calculate epsilon as a function of n hat, and n hat is basically discretized up to, let's say, 1,000 different direction. And you somewhere are suppressing all the information in the longitude, I mean, in the, different, at the depth of the detector, like calorimetric in different parts of the, you're just sandwiching all of them into a single flow. Is that what you
Yeah,
are?
yeah, right. So that's my representation. So if you want to think about a calorimeter tower, I am projecting out all the segmentation information. But from a, this is a theoretical talk. So it's not segment. You can really imagine these as being delta functions, and so I can have infinite resolution in my calorimeter. But yeah, if you want to think about this practically at the LHC, you can imagine just taking all the calorimeter cells, projecting them down, and then just talking about the energy density in calorimeter cell space. And so this is a very standard picture. People who talk about jet images in machine learning, they use this representation.
I
but what's cool is that
but
I actually don't need to, yeah.
Yeah, sorry, what I meant by that, if you have the track elements and the tower elements, all the different pieces, I mean, you start out with a suppressing information, but it's fine for you. I mean, for now, is that? I mean.
Yeah, so I'm imagining an idealized picture where you can imagine I use the tracking and the calorimetry together to make my
particle flow stuff
flow
and
reconstruction.
Okay, I see.
And then I'm saying like this is like the true best estimate of the energy density. Okay. So in particular, if I have charged pions, I get fantastic angular resolution, even though the calorimeter resolution is poor.
Right. Okay.
So, but I'm imagining as if I had perfect information. Does that answer your question?
Yeah. So I can think of just Monte Carlo final state events for now. That's like a, yeah.
Yeah, correct. And the question before about masses, also I could extend the story to have perfect information about what the velocities of the particles are. So it's really like Monte Carlo truth information. And I'll show you some comparisons of Monte Carlo truth to collider data, just so you can see how close the comparison is. That might give you some intuition. That will be, maybe 10 slides from now.
Yeah, great, thanks.
Right. Okay, so I started asking the question, when are two collider events similar to each other? And one way to ask that is, can I quantify how close these collider events are? So this is one collider event from CMS, another one from Atlas. Of course, they're on different sides of the LHC ring, so you can say that these are 8.5 kilometers apart, but that's obviously not a useful notion of distance in this case. But here we notice that these are topologically similar events. This is a multi-jet configuration. This is a multi-jet configuration. We have a bundle of particles over here. We have a bundle of particles over here. There's some similarity between these two events. And we would like to give a number to how similar these two events are to each other. As I said, I'm going to be focusing just on energy flow. So really what I'm talking about is the similarity of two energy flows. So here we have, again, this head-on view of a jet. In this case, this is a jet created by a boosted top quark, which famously has a three-prong topology. And here's another boosted top quark that has a three-prong topology. And I want to try to give a number to say how similar these two jets or two energy flows are to each other. And there's a whole literature in geometric data processing for talking about the similarity of energy flows. And it goes under the name of optimal transport. And there's a concept called the Earth mover's distance, or the one Wasserstein metric, which says that the similarity of two energy flows can be quantified by how much work, in quotes, you'd have to do to rearrange one energy pattern into the other. So let me run this movie again. So what we're going to have up here is we have the transportation plan for rearranging the red jet into the blue jet. And I would have to do exactly the same amount of effort to rearrange the blue jet back to the red jet. And in this case, the amount of work I'd have to do, quantified in giga electron volt units, is 125 GeV, which is just coincidentally the Higgs boson mass. This has nothing to do with the Higgs, but it's of the order of the top quark mass, which makes sense. I have one top configuration. I need to merge it into another top configuration, and order of magnitude of the top mass is how much work I have to do to rearrange one configuration to the other. So this idea of optimal transport. Yeah, go on.
Does this automatically include the symmetry factor of an event, the symmetry of an event?
As I've defined it right now, it does not, but there's another concept called the tangent Earth mover's distance, which what you do first is you actually apply all the various isometries. So in this case, you would take this blue jet and first rotate it to make it look more like the red jet, and then compute this transportation plan. So here I'm not showing that additional isometry step, but there's a very natural generalization of this to include those isometries.
Okay.
And what that corresponds to is changing the effective dimensionality of your space. That is, if you mod out by all the isometries, you basically reduce the effective dimensionality by the number of isometries you include. I'll explain a little bit more about that later, so you can ask your question again if it's not clear. So this idea of optimal transport shows up all the time, though I only learned about it relatively recently. This actually goes back to ideas in the 1780s. A French mathematician who wanted to know if you have a pile of dirt, which I guess in French they have a special word for pile of dirt, which is déblai, and you have a trench that you're trying to fill in, and apparently there's a special French word for that, the remblai. And you want to basically convert this pile of dirt and fill in these holes. You want to figure out what's the optimal way to do it. What is the minimum amount of work, that is an amount of stuff, in this case dirt, times distance you have to move it, to make one distribution look like another distribution. And this shows up all over the place. It was more formalized by Wasserstein in the late 1960s. And it shows up in image processing in the kind of 1980s and 1990s. More abstractly, what we're trying to do is take this blue distribution and make it look like the red distribution and ask how much stuff I need to move a certain distance. And as long as you have some notion of weight that's additive and some notion of a ground distance, this defines the distance between distributions. So in the particle physics context, these weights will be energies and the distances will be distances in the rapidity azimuth plane. But you can imagine many other types of data sets with their appropriate weights and distances. And anytime you have two distributions that you're trying to compare, they could be probability distributions, they could be distributions of dark matter in a halo. Anything that has a notion of weight and a notion of distance, you can define a distance between the distributions via this optimal transport idea. So in the context of particle physics, instead of the Earth mover's distance, that is moving dirt around, here we want to move energy around, so the energy mover's distance. And we have to have an optimal transport between energy flows. So here are those same two red and blue jets that I showed you before. And now the black lines show you the optimal transportation plan for converting one jet into the other. And the energy mover's distance has units of GeV, and it has two terms. It is the cost associated with moving energy. F is the amount of energy that needs to be moved. Theta is the angle that it has to move between. And for units, I have to divide by the jet radius for this to have units of GeV. And then we have to consider the case that two jets don't necessarily have the same amount of energy, and there's a penalty term for the energies being different. And if you have this optimal transportation plan between energy flows, if you have this notion of distance between energy flows, then you can now talk about an abstract space. So going from this original geometry of the collider event geometry to an abstract geometry, I can define an abstract geometry that has a metric, that is a notion of pairwise distances between points. So I have my red jet, I have my blue jet, now represented by single dots in this abstract space of events. I can imagine a third green jet. And what makes this a metric is that it satisfies the triangle inequality. So it's positive, and the distance between red and blue is shorter than the sum distance of red to green and green to blue. And there's some subtleties about choosing this R parameter appropriately that I won't go into right now. But now, using this optimal transport idea, I can now define rigorously a notion of distance between events, and that's what I'm going to be using for the rest of this talk. So just to show you a few more videos of this in action. So if I want to show the similarity of three energy flows, here we have a red jet, a green jet, and a blue jet. Again, these are single points in this abstract space. And now I'm showing the transportation plan to convert one to the other. And that then corresponds to a distance in this abstract space. And you can check for yourself that these three events actually satisfy the triangle inequality. I plotted those distances here. It's an interesting question to ask, what's the curvature of the space? What's the dimensionality of the space? And I'll show a little bit of that coming up. Okay, but this is when events are similar. They're similar when they're separated by a small energy mover's distance. And we can now triangulate an abstract space by figuring out for a collection of jets, what is their pairwise separation, and then triangulate an abstract space. And here's a link to a news article from the MIT News that likens this to trying to reconstruct a social network. And the number of nodes connecting you and your neighbors, which is kind of a reasonable analogy here. We're trying to now find kind of the social network that represents the relationship between jets to each other. Things that are close in terms of not needing much energy mover distance are close in this network. Things that are far apart are further apart. Okay, so we now have this notion of a metric, and what can you do with it? So let me just give a few examples because I want to focus on this more recent work, but here's some things you can do with the metric. So one thing you can do with the metric is you can talk about the dimensionality of your space. So intuitively, if you want to figure out the dimension of the space you're living in and you're a point, you can ask, how many neighbors do I have at a given distance r? And if the number of neighbors I have grows to a certain power, that tells me the dimensionality of my space. So if I'm living in a space that as I go out in distance, the number of neighbors grows like the square of the distance, then I would be living in effectively 2 dimensions. But what's nice about this notion of dimensionality is that it allows you to talk about dimensionality that can change with scale. So if I just invert this relationship, I can figure out the dimensionality as a function of the distance r. And here's an example of a spiral geometry, which highlights this idea that the effective dimensionality can depend on the resolution at which you're analyzing your space. So if I zoom really close in, I have effectively points filling a plane, so that's effectively 2-dimensional. If I zoom out, I now see that actually these things are more aligned along a line, so that's 1-dimensional. And if I zoom out more fully, then it kind of starts filling the plane again. And if I zoom out really far, then I eventually get just a single dot, and I have effectively a 0-dimensional space. So this is an example of a data structure that has dimensionality that changes with scale. Now, intuitively, QCD has a dimensionality that changes with scale. We talk about things like anomalous dimensions, and I can now take my space of jets, and I can now do a QCD calculation. Now, not as a function of distance scale, but now as a function of a momentum scale. And now I can say, as a function of scale, what's the effective dimensionality? Again, I'm using this energy mover's distance idea, but now I'm just doing a QCD calculation of it. And at short distances, effectively, all I can see is a single parton. And if I do my isometries to align that parton to always be pointing in one direction, then effectively I have a 0-dimensional space. And so I have a 0-dimensional space at high scales. And then as I start resolving more and more emissions, I start getting a non-trivial correlation dimension. Shown here in dotted lines is a leading logarithmic calculation where you can see that dimensionality scales logarithmically with the scale Q. And it depends on whether I have quark jets or gluon jets. And the overall dimensionality also depends on the strong coupling constant. So this is kind of an interesting way of thinking about RG flow, but like an RG flow as defined by a dimensionality induced by this energy mover's distance. You can see the Pythia calculation in the dashed line. And what we actually also did is we looked at public data from the CMS experiment, which is some admixture of quarks and gluons. And so not surprisingly, what we see is we see a dimensionality somehow between those two curves. In black is real data, in yellow is simulated data, and in blue is actually the truth level output from the Monte Carlo. And you can see that what the detector does is it kind of smears things out and generates more effective dimensionality, kind of it generates a half extra dimension. But you see this expected trend from the theory calculation. And if you resolve 400 GeV jets, you resolve it at the 10 GeV scale, you're talking about an effective dimensionality of 4 or 5, which is kind of interesting. It's a space triangulated by this energy mover's distance, and this is an interesting probe of the dimensionality of QCD.
Sorry, these
Jesse?
jets are jets in
Yeah.
the multi-jet sample or D plus jet sample? I mean, which kind of jets are these?
Excellent. So this is jets obtained just from garden variety dijet collisions, where I've isolated 400 GeV jets in very, initial 2011 7 TeV proton-proton collisions. So this is just totally garden variety jets. and we just take that sample of jets. In this case, we're looking at 30,000, I think, 30,000 jets, and we're estimating the correlation dimension through this formula. Was there another question?
Yeah, I think I sort of missed the link between the energy distance and Q here. Is Q like proportional to the energy distance compared to lambda Q3 or something? Or how should I think? Yeah.
So Q is literally the energy mover's distance, and it's saying that if I look at jets whose energy mover's distance is 100 GeV, let's say, and I take the derivative, the logarithmic derivative of the number of jets that I see that have that separation. So basically I look at 100 GeV, 101 GeV, and I compare how many neighbors each jet has, then that gives me an estimate of the dimensionality. So Q is the energy mover's distance. And apologies that I don't have the formula on the slide for it, but it's basically this exact same formula here, just replacing R with Q, and Q being the literal energy mover's distance I introduced before.
Yeah, okay.
That makes sense?
Yeah, it's okay.
Okay.
So you're taking all the neighbors.
Sorry, so there was another question which I can't hear. It's quiet.
So you are taking all the neighbors with this energy movers distance less than Q? Is that what you're doing?
Exactly. So
Yeah.
I find all the events where the number, so this is the number of neighbors within a ball of radius R. So this is the number of neighbors within a ball of energy movers distance Q, and then I take the logarithmic derivative. That's exactly correct. Yeah.
Okay, thank you.
Okay, so what else can I do when I have a notion of a metric or a distance? I can use I can try to find the most representative jets, the jets that are most typical for my event sample. So here is the plot that I showed you at the beginning of my talk. And what I'm doing is I'm taking this 4 or 5 dimensional space and I'm projecting it down to 2 dimensions using a technique called T-SNE. And so the gray blob here is the density in this projected space of 30,000 jets. But trying to look at 30,000 jets all at the same time is basically impossible. So I've sprinkled in 25 jets on top of this gray blob. These are the 25 most representative jets. And what do I mean by most representative? These are the 25 jets that if I take my event and cluster it using an algorithm called K-medoids, this is the K configurations that best represent my space of 30,000 jets that I'm plotting, where the size of the circle here corresponds to the number of nearest neighbors. And then the example here, the medoid, is just the example jet. So here in this highly dense region where the gray is dark, we see very garden variety, typical QCD jets, single prong of radiation at the jet core. And then as I go further out, I find more exotic jets. So here off further away, I see 2-prong jets with equal energy sharing. Down here, I see 2-prong jets, but with unequal energy sharing. Up here, I see 2 prongs whose angle has gone close to 0. And there's a sense mathematically where if I understand the 25 representative jets, then I've actually understood the full space up to a given accuracy. And so this is a concept from computer science called a core set that is a representative subset of your data sample that captures the dynamics. So really, if you could understand these 25 jets, to some degree, you've understood what QCD jets at 400 GeV, what they are, and understand their properties to some accuracy. So this is finding the most representative jets. I can do the opposite and find the least representative jets. So here I'm trying to take each individual jet and find its average energy mover's distance to the rest of the data set. So the most typical jets are kind of in the core of the distribution, and they just correspond to these single prongs. And then I can find the major outliers. And so the outliers, the ones that are really far away from all its friends, those are either, just the tails of QCD, or potentially, exotic new physics signatures that are far away from the bulk of the distribution. So you can imagine using techniques like this as a kind of anomaly detection scheme to find strange-looking objects in this space. So I'm happy to talk more about this if you're interested. So I just went very quickly through these examples of how you might use this metric. But what I want you to take away from this part of the talk is the answer to the question, when are events similar? They're similar when they have a small energy mover's distance. And I can use this energy mover's distance to triangulate this space. And what I'm going to be doing in the rest of this talk is using this concept to expose a hidden geometry that's been with us in particle physics for half a century.
Jesse, can I pause you? So can I stop you for?
Yes.
Yeah. So in the last slide, how well does it work compared to standard? It's not standard, but more or less autoencoder stuff. Is it comparable?
Oh, it works. It works
better?
terribly because we haven't optimized it at all. Okay. So what this is doing is just saying, here's the average EMD to the data set, but that's not really what you want. What you want is you want to isolate not just the average, you want to isolate regions of phase space. And really what's more important is that there's like a notion of local dimensionality. Right. And you want to say that there's too many jets or too high of a dimension in some localized region of phase space. So that's really what you're trying to get at.
Right.
So this by itself is not good. But we're working on ideas that generalize this, which seem to work better. But I think maybe the takeaway from this is just to say, look, I can make a plot of a histogram of an abstract distance in that space, and I can use this medoid idea to see the representative examples. And having histograms like this really helps you gain an intuition for what QCD looks like. So this three-prong jet here, I can tell you this is not a top quark, but it looks like a top quark-like configuration. And this is basically telling you, yeah, with tiny probability, there's a chance for ordinary QCD to give rise to this radiation pattern. So I find plots like this really helpful for building intuition about this space. As an anomaly detection scheme, it's not quite there, but we're working on it.
Okay, got it, thanks.
Right.
Jesse, I think I missed something. If you go back one more slide. So that, yeah, right, I missed that. So it's a dimension, it's a scatter plot in
yeah, good. Let me try to narrate again what this is, because this is very unfamiliar. Okay, so first let's go back one more slide here. I've told you that the dimension of this space is 3, 4, 5 dimensional if I resolve it at like a reasonable scale. Okay, and our brains can't process 3 or 4 or 5 dimensions. So what I'm doing is I'm using an algorithm that takes these 30,000 jets and projects them down into 2 dimensions. So this is again this T-SNE idea, where the distance in this space is as close as you can do to the distances in the original space, given the limitations that you're projecting down to 2D. And then I'm making a density plot in that space, and that gives me the gray blob. So I probably should have made an overlay without these 25 circles on it, but just imagine this gray blob by itself. That is the density of jets in this abstract space as projected down to 2D. So that's step 1. So let me just pause to see if that makes sense to you.
But what are the dimensions? So this one
the
of
dimensions,
them
good.
Yeah,
the dimensions are my best 2-dimensional approximation to a fractally dimensional space. So imagine that you have, in general relativity, we're used to thinking about, a fixed metric that has fixed coordinates with a fixed dimensionality. And now I'm talking about a different type of metric, not a metric that has a notion of like, of coordinates, but a metric that's defined just by pairwise distances. And I want to basically lay down points such that the distances in this 2-dimensional space, which is learned, this is a machine learning technique, so this is a learned space, that the distances in this space between this point and this point is as close as possible to the original energy mover's distance between those points. So it's a crazy learned manifold space.
Okay,
that is just my attempt to see things, yeah.
Yeah, so let me just try to understand this. So you have some very high dimensional space in which there's some cloud of points. Okay.
Yes.
And you're trying to see whether there's a 2-dimensional manifold lying in this high dimensional space, which more or less captures the distance information between the points. Is that what you're trying to do?
That is exactly correct.
And this manifold is not something that you know a priori, but you use a machine learning technique for that.
That is correct.
Okay, thanks.
Yeah, so that's the gray blob. And then that gray blob, I have no intuition for it. So I want to know, hey, give me example points in that gray blob. And these 25 points are representative examples as shown here. So the gray dots here correspond to my 30,000 points, and I'm finding the representative orange stars or orange points that capture the dominant features in this space. Okay, other questions before I move on? Great, and by the way, I appreciate the questions. It's otherwise challenging to give a remote talk. It feels like speaking into a black hole. So I appreciate the feedback. Okay, so for the remainder of this talk, I now want to try to answer the question, or at least start to answer the question about what can be geometrized.
Excuse me, Jesse, pretty directionless question. I mean, there's nothing, is there something special about this energy mover distance, or did you try something else and this works out best?
Good. As you're going to see, this energy mover's distance is very special. We tried other things, and there's other things that have the notion of a metric that is satisfying the triangle inequality. And there's actually a whole multi-parameter family of distances that make sense. So here in this formula, if I take this theta and I raise it to a power, that turns out to also be reasonable. But what you're going to see in this part of the talk is that it seemed like this energy mover's distance was kind of arbitrary. And yeah, okay, good, nice to be able to define this notion of distance. What does this have to do with anything that we've known about QCD? And the answer is, it's amazing, the level of correlation. And you'll see this coming up. But you can imagine a whole industry of people trying to come up with different notions of distance. In fact, there's a couple of papers that have been exploring that in the literature recently. There are other interesting notions of distance that one might like to explore, but this one seems to be special, and you'll see why in a moment.
Okay, thanks.
Okay, so what can be geometrized? So, when we teach collider physics 101, here's the kind of the master formula for figuring out the cross section for an observable. It involves a sum and an integral of our phase space. It involves calculating a scattering amplitude. It involves choosing an observable. And what we're going to see is that the concepts of phase space into this abstract space. And there's also things related to cross sections and things related to amplitudes that have a mapping as well, though those have not been as fleshed out, but I'll try to give you examples in this last part of my talk to highlight these connections. Okay, so let's start with phase space. And you can ask, what replaces ordinary Lorentz invariant n-body phase space? And since I'm working with a space, I can talk about manifolds in that space. And the natural thing that replaces Lorentz invariant n-body phase space is just the manifold or the set of all n-particle configurations. So just to remind you, I'm taking an event and I'm mapping it to a single point. And then I can talk about collections of events. And I can think about, for example, the collection of idealized one-particle configurations. And just as a technical point, one difference between Lorentz invariant n-body phase space and this manifold is that actually it turns out to be natural to not impose energy momentum conservation in this one-particle manifold. So here I have event configurations that obviously don't conserve energy momentum, but I can consider all possible one-particle configurations. Or I can consider all possible two-particle configurations. And what's kind of interesting, and I'll emphasize this a little bit more, is that when two particles become soft or collinear, you actually revert down to the one-particle manifold. So there's actually a nesting of these n-particle manifolds. Similarly, I can talk about a three-particle manifold. And this collision from Aleph obviously doesn't live on the one-particle, two-particle, or three-particle manifold. It lives in a higher dimensional manifold. But you can imagine trying to use these manifolds and approximate events as how close they are to those to these lower dimensional manifolds, and we'll see an example of that in a moment. Okay, so the natural thing to kind of think about with, instead of Lorentz invariant n-body phase space, are these n-particle manifolds. And why do I say that this is natural? The reason why I say this is natural is because of the question about when are two events the same. So again, we're talking about events in terms of their energy flow. And as we're all familiar with this energy flow is unchanged rather by infinitesimal soft and collinear emissions. So if I start off with a jet and I add a zero energy particle to it, that clearly doesn't change the energy flow. It changes the number of particles, but it doesn't change the energy flow. Similarly, if I take a particle and I split it into two, that doesn't change the energy flow. But ordinarily, when we're talking about Lorentz invariant n-body phase space, it's annoying because when I have a softer collinear emission, I basically have to work with a higher dimensional Lorentz invariant n-body phase space. But if you think about this energy flow space, infrared divergences end up living together. Why is that? Well, I have some process, let's say, that gives me n particles, and I look at a virtual loop diagram. Virtual divergences live on that n-particle manifold. You can imagine this as being like the Born phase space, and then a virtual diagram still lives in that same Born phase space. Real emission diagrams, where I have an emission, let's say, of a gluon with a momentum fraction z and an angle theta, that lives in this higher dimensional n+1 particle manifold. But in the soft and collinear limits, that is the limit where z goes to 0 or theta goes to 0, and I have singularities as governed by the Altorelli-Parisi splitting function, or by the dipole formula in the soft emission case, you end up reverting back down to the n-particle manifold. And so what's really nice about this energy flow space is that this nesting of these manifolds tells you that real and virtual divergences essentially live in the same space. So that's why this way of thinking is in some sense more natural than thinking about Lorentz invariant n-body phase space, because the divergences end up coexisting in this abstract space. And that's one of the advantages of working with this energy flow. So yeah, go on.
So on a related thing, instead, I mean, you started out with define the phase space. I mean, the phase space of what you observe in a detector geometry. But if you, for example, instead of doing that, if you have lived in, let's say, energy correlation space or in n subjettiness space, right? Then it's automatically, it satisfies the criteria that you are already in some sense. I mean, it's somewhat abstract space, but in this multidimensional space, things are as well defined as you'd probably get in that scene, right? I mean, in that sense, it's already somewhat solved.
Good. So let me just reiterate Tuin's point. So Tuin's point is that if I worked with, instead of this energy flow space, if I worked in the space of energy correlation functions or the space of n-jettiness values, I would automatically regulate these real and virtual divergences, and that working in that space is also quite natural. And these things end up being dual to each other. So we are going to see that this n-particle manifolds and n-subjettiness or n-jettiness end up being very closely related to each other. So I 100% agree. And if, in some sense, what I'm saying is exactly what you're saying. And there is probably some more formal duality between these languages that we haven't uncovered yet. So just to make this maybe a little bit more precise, when we talk about configurations or talk about observables that combine real and virtual divergences correctly, so that you get finite answers, we call that infrared safe or infrared and collinear safe, which basically, for the purpose of this talk, you can think about just as things that are calculable in perturbative quantum field theory. And what's special about this space induced by the energy mover's distance, as I've defined it, is that infrared and collinear safety is, with asterisk, but I'm happy to talk about later, just corresponds to observables that are continuous, that is continuity in this EMD space. So if you remember from real analysis, what continuity is, it involves these kind of epsilon delta proofs. And if things are within a delta ball in this EMD space, that the observable is within an epsilon ball in the observable space, that corresponds to continuity. And the previous notion of infrared and collinear safety actually just maps on beautifully to continuity in this EMD space. And this asterisk corresponds to different notions of continuity which map onto different things that have been said in the literature about what is or not calculable in perturbative quantum field theory. And if you want a term to look up, things that are calculable perturbatively in the ordinary sense satisfy a type of continuity called Holder continuity in this EMD space. And so Tuin's point about that I could have also used n subjettiness space or n-jettiness space to map things out is correct, but I really like this space because there's a notion of continuity in this space that maps onto traditional notions that have already appeared in collider physics. And in some sense, you know, the EMD seems to bind the natural geometry for massless gauge theories because of this fact. What I don't know how to do is how to define amplitudes in this space. We usually think about amplitudes as living in Fock space. I do not know how to talk about amplitudes in this space, nor do I know how to actually do integrals in this space. Though there's a whole literature of people doing integrals in these kind of Wasserstein spaces that's being developed right now, and we're hoping that we can take some of that work that's being done in the kind of more computer science side and see if we can understand some of these things in this language. So I can geometrize infrared and collinear safety, and work in progress is trying to understand what do amplitudes mean, because amplitudes are usually defined with a fixed n. How do I talk about amplitudes for energy flows? And that's an open question. Okay, so this gives you a sense of how the notion of phase space gets geometrized. What about observables? And I've already kind of hinted at this at the beginning of the talk, that I can use manifolds to understand what observables are. So I have one event that's a point in this abstract space. I have this manifold of events that can correspond to some set of events. And the distance of closest approach between an event and a manifold is one way of defining an observable. So an observable, I take in one event and I get back a number. And here, what I want to do is I want to say, okay, let me look at the energy mover's distance between all possible configurations that live on that manifold, and say, what is that distance of closest approach? And that is one way of defining an observable. You can imagine defining observables as the average distance as well. There's other things you could do. You can imagine a lot of creativity in coming up with these manifolds. But it turns out that observables that we already know and love have a translation into this distance of closest approach. So one of the first ones we figured out is thrust. So thrust is a statement about how dijet-like is an event. So again, I have my event, single point. I want to think about two particle configurations. And for thrust, it turns out that I want to think about all possible back-to-back two particle configurations, where where, as I mentioned, it's more natural to not think about energy momentum conservation here. So these are two back-to-back configurations that don't necessarily preserve energy momentum. And now the distance of closest approach between that event and that manifold, that is thrust. So the distance of closest, or the point of closest approach turns out to be related to the thrust axis. The distance itself is related to thrust. And the translation is not so difficult. The translation is you take this T, 1 minus T over twice the center of mass collision energy. That's the original thrust. And here I tried to find as the most grainy old plot I could of thrust from let's say Aleph, just to emphasize that this concept has been with us for a while. And the original formula of thrust, as written down, for example, by Eddie Fari, this is mapped onto this EMD notion of thrust. And so this gives you some sense about why this choice of energy movers distance is natural, because it maps onto things that we have seen in the past. But now that you have this way of thinking about what thrust is, how dijet-like is an event, you can now think about other more interesting manifolds and ask questions about the distance of those manifolds. And maybe the simplest case is how isotropic is an event. So I can think about the isotropic configuration, that's just a single point in the space. And I can think about what's the distance, the closest distance to the isotropic configuration. And this is work that I did with Kari Cicerode, who's at Harvard, and we defined this distance to uniform. And it's kind of cool. It's something that you can define just as the EMD to the uniform configuration. And what you see is that this is an observable that has huge dynamic range in its ability to distinguish different levels of uniformity. So here I have a histogram estimating this event isotropy for a QQ bar configuration, which is very far away from 0, so it's very not isotropic, and then going up in 10 body, 25 body, and 50 body uniform phase space, and you see that this observable is able to distinguish between different levels of uniformity, where even 50 body phase space is not actually uniform. It still has a non-trivial distance away from 0, which would correspond to the perfectly uniform event. So this is a kind of new way of thinking about defining observables as distances to interesting manifolds. What about n-subjettiness or n-jettiness that we've discussed before? So this is something that I worked on, almost a decade ago, and people would complain to me about this formula. I mean, if you stare at it long enough, maybe it's intuitive that this n-subjettiness, you take in a jet and you ask how well aligned is your jet along n-jet axes. So for example, tau3 is basically saying find the 3 axes that are most similar to your jet. 2-subjettiness is find the 2 axes that are most similar to your jet. And here's this formula, which I think when we first wrote it down, inspired by work by Ian Stewart, Frank Tackman, and Walter Weilevine on n-jettiness, when we first wrote it down, people were like, well, why'd you write this down? You could have written many other things down. Why this thing? Well, this thing turns out to be the one that maps beautifully, geometrically, onto the distance of closest approach to the n-particle manifold. And so this idea that n-subjettiness is the distance to the 2 or the 3 particle manifold, or more generally the n-particle manifold, that's because of the particular choice of EMD that we chose. And this formula, to my eye, is a lot more beautiful and a lot more intuitive than the one that was shown before, once you have this notion of manifolds in this abstract space. What we ended up doing in this paper that was on the archive a few months ago is seeing that a bunch of observables in the literature correspond to distances to n-particle manifolds. So n-jettiness is the distance of closest approach to the n-particle manifold for entire events. There's an algorithm that I developed with collaborators called XCone, which is actually the point of closest approach on the n-particle manifold, basically finding the point that best approximates that event, but restricting to that n-particle manifold. Sequential jet recombination algorithms, like the KT clustering algorithm, correspond to sequentially taking an event and moving it, stepping down to the n-1, n-2, n-3 particle manifolds, and each of those iterations corresponds to steps in a sequential jet recombination. So this notion of distance and this geometric language has been with us for quite some time, and corresponds to things that are well known in the literature, now unified in this geometric language. So actually, Rishi, how much time do I have? I see we're already at the hour. There's been questions, and I'm happy to continue, or just try to wrap up quickly. How much time should I aim for?
Maybe around 5 to 7 minutes, if you can wrap up.
Yeah, sure. Okay, so just because of time, let me not talk about how Pileup mitigation actually turns out to be actually moving like geodesics on the space. There's some beautiful kind of stained glass windows that correspond to different geometric strategies. But let me just conclude by showing you maybe the most kind of radical version of this. So just to kind of end this part of the talk, so what can be geometrized? Concepts like infrared and collinear safety, various observables, jet algorithms, Pileup mitigation schemes, they all have this geometric interpretation. And it's kind of remarkable to us how already, in some sense, people already had this intuition. They just never wrote it down using this particular energy movers distance. And now this unifies concepts that have appeared in the past 5 decades of collider physics. Okay, so I want to spend the last 5 minutes just asking the question, how far down does this rabbit hole go? Okay. And hopefully this will be inspiration to you to kind of think about maybe incorporating these concepts into your own research. So we started off with direction space. We had directions in the rapidity azimuth plane, and we had a notion of angular distance between points. And what we did is we took those directions, we weighted them by their energy, and we took this point cloud of weighted directions, and we map that onto a single event. So this is the usual geometry that's now been mapped to a single point. So now let's look at this abstract space of events. I have an event. Okay, the event happens to be a whole distribution of energy, but I have this notion of distance defined by the EMD. And now I can go deep down a rabbit hole by repeating this procedure. So what's needed is to have weights. What is the natural way of weighting events? Well, I can weight events by how often they're produced in a collider. So I can weight them by their cross-section. So now I have weighted events. And a collection of weighted events, what does that correspond to? Well, I would argue that this corresponds to what we would colloquially call a theory. A theory is something that tells you what's the cross-section for every possible event configuration. Of course, this is not theory in the ordinary quantum field theory sense, but I would in some sense argue that as far as energy flows are concerned, this is the complete information about a theory. What is the energy flows and with what cross-section are they produced? But now you can rinse and repeat. And now you can talk about a theory. A theory is a distribution weighted by cross-sections over the space of event configurations. I can try to distort the cross-sections from one theory to another, and that defines the cross-section mover's distance, stylized as sigma MD. And here's a formula for what this cross-section mover's distance is. And this cross-section mover's distance gives me a natural distance between theories. And now your brain starts going, off and thinking, well, geez, if I use the energy mover's distance to define engettiness, I could use this cross-section mover's distance to define something like the K eventiness. And in fact, this K meteoroids thing that I showed before turns out to be related to that notion. But let me just close with one example coming from QCD, which I think is helpful to think about. So this is an example of a collision event, not in proton-proton collisions, but in heavy ion collisions, where we have lead nuclei colliding, making a quark-gluon plasma, and the jets that are coming out get quenched by their passage through this hot, dense medium. Okay, so what does this have to do with event geometry, theory space? What does it have to do with this? Well, you can imagine QCD in vacuum as corresponding a theory that gives you various jet configurations. But if I take QCD at finite temperature and density, and I think about, okay, QCD in medium, that gives rise to jet configurations which are different than the ones that I had in vacuum. And one of the big questions in nuclear physics is trying to understand how are jets distorted from going from vacuum to in medium. And I can use this cross-section mover's distance, defining an optimal transportation plan that defines a mapping between in medium jets and vacuum jets, and trying to figure out, in some sense, when I see a jet in medium, where did it come from in the vacuum theory, or what's my best estimate using this cross-section mover's distance? And kind of remarkably to me, this story that I just told you, I in fact kind of accidentally came to in work that I did with Jasmine Brewer, who's getting her PhD this year at MIT, as well as Guillermo Milano, who's at Lisbon and CERN. We happened to define precisely this story. It's a procedure that we call quantile matching, but we had no idea that it had anything to do with this theory space. And it turns out that something that we proposed in 2019 for analyzing the way that lead-lead data can be kind of mapped onto proton-proton data turns out to be equivalent to following this geodesic and theory space. Again, this idea with Jasmine and Guillermo, this came out first, and we thought it was very natural. And now we have this more geometric way of realizing, oh, this really is the, in some sense, natural way of talking about this conversion from one theory to another. So it's very satisfying to see this geometric strategies coming up over and over again.
Okay, so on a, just I know time is short, but on a quick question. So the PP plot and your lead plot, the PP plot with let's say 400 pileup crap. Okay.
Yeah.
Is it in your distance? Does it fall in between, or how, or keep adding pileup? Does it marches to it, or how do you see that?
Oh, so in this particular plot here, this is a plot that's taken after having done an underlying event manipulation scheme. So actually, there's no distortion here if I did a perfect Pileup mitigation. But you're correct that you can think about this exact same kind of transportation plan in the context of Pileup. So you can think about one theory as being the theory without pileup and what the cross sections for various observables would be. The other theory is being the theory including pileup contributions. And you could try to do this exact same game as a type of pileup mitigation scheme. We have not tried that, but that's an interesting thing to think about, and it would be interesting to see how that mapping would go. But here, this particular plot happens to be one where you've already done an underlying event subtraction.
Sorry, can you? I didn't follow this last statement of yours. So jet quenching basically says that T and T prime are different, I guess. But what do you mean by saying that jet quenching gives the geodesic between these two points?
Yeah. Good. So I have one theory that gives rise to certain jet configurations, and what that is, these symbols are supposed to represent individual events weighted by their cross section. Do the same analysis, QCD and medium, I get a different set of configurations. And ideally, what you'd like to know is how do I get from a jet here to a jet there? So for example, if I want to understand transport properties of the medium, I would like to basically be able to take one jet here and watch it convert into the jet here. Now I can't do that because of course I can't actually go and find out what really happened. But what I can do is I can make a guess. I can make a guess that the way that jet quenching proceeds is one that doesn't distort the energy flow more than it has to. And then this cross-section mover's distance is basically trying to say, well, what is the optimal way of distorting each of these jets to look like each of those jets that involves the least amount of movement of cross-section and energy flow? Now, it's not guaranteed that corresponds at all to what the real jet quenching is doing. But what I did in this paper with Jasmine and Guillermo is we actually showed that this procedure of kind of transporting the gray curve to the black curve, that under certain jet quenching models, in particular this Joule Monte Carlo, actually corresponds better than you might think. That is, the distance of closest approach actually is a good proxy for what's really going on if you had truth information.
Okay.
And ideally, you'd actually figure out maybe this cross-section mover's distance isn't the right one. Maybe there's a better distance that actually does a better job of reconstructing what's really going on. But this is a data analysis strategy that happens to, under certain assumptions, map on very nicely. And in fact, there's a limit. If jet quenching is always monotonic, that is, you can never change the order of jets in terms of their PT by a jet quenching. Under the monotonic assumption, you can prove that this is actually the optimal thing to do. But more generally, that's not true. And so this is just a proxy for what we think is going on. That makes some sense?
Yeah, okay.
It's very abstract. And again, this paper says nothing about transportation plans or anything like that. It just happens to be that it's the same thing. That is, this notion of transportation plans is much more ubiquitous than you might have otherwise thought.
So I have a question here. So supposing two people come to you with different models of the heavy ion physics, and they give you different mappings between the PP jets and heavy ion jets. What would you do to distinguish?
To figure out which one was better.
Sorry?
Yeah. You're saying, what can I do to figure out which one was better or which one maps better? Is that what you're asking?
No. How do you distinguish between them? You wouldn't know which one is better.
Well, so I would argue that actually you can figure out which one is better if you have, for example, a sample of Z plus jets, because the Z is a proxy for the hard scattering scale.
Yeah, sure. That we already know. Know. So is there?
But you can do more. Yeah, no, but you can do something more than that. You can say, I now do this transportation plan on the Z plus jet, and I look at the resolution that I obtain using Z plus jet as a benchmark. So what you can use is you can use Z plus jet as a control sample, not just using the Z as the estimate, but actually seeing whether when you do this transportation plan, what's the degree of correlation with the ZPT. So it's going a little bit one step further using that Z information, and using that as a cross check. And there's other ways of actually doing cross checks. But I think your point more generally is a good one, which is that what I'm talking about in this talk are data analysis strategies, and the mapping between those data analysis strategies and the fundamental theory of what's really going on is not. I would say that we haven't yet demonstrated that we have that precise of a mapping. Even in what I was talking about earlier about mapping infrared and collinear safety onto this continuity and EMD space, we haven't really shown that you can do calculations yet in this space, and we haven't shown a way of replacing, for example, Feynman diagrams with something else. But I think it's giving us hints about how we might think about it. And I would be thrilled if people started using this notion of mapping between jets and transportation plans between jets as a strategy for thinking about heavy ion collisions. And maybe that would help us figure out more about the underlying theory. But ultimately, you know, I don't have a suggestion at the moment that's any different than try these techniques out on various different generators, see which data analysis strategy maps onto those generators, and then just collect all the data you can to try to figure out what the correct parameters of your model are, and do the standard comparisons that we're doing. But this is it inspires new data analysis strategies that, at least for certain models, end up giving you more closely the parameters of those models. So in the case of Joule, for example, this quantile matching can be used in a way that seems to map on pretty well to the kind of knobs that you can tune in Joule. Okay, so let me just wrap things up, and then I can take further questions and stick around for longer if people want to ask more. But I just want to make sure that you got the big picture summary of what I just told you today, because we went through a lot of material. So first, what is a collider event? A collider event is an unordered set of particles that describe the energy flow away from the collision point. And this perspective, I have some backup slides about the relevance of this for machine learning, but this is one representation of collider events, and the one that in some sense is most sensible and most robust for massless gauge theories. When are two events similar? They're similar when they are close in the geometric space, triangulated by the energy mover's distance. And so the fact that we have this notion of an abstract space, this is a new tool that we can use, and I hope this tool inspires you to think about what it might be useful for in work that you're doing. And then finally, what can be geometrized? Many concepts and techniques in quantum field theory and collider physics from the last half century turn out to have a direct mapping into this space. And my hope is that the next 50 years of collider physics will be inspired by some of these geometric strategies. So let me stop there. Thank you so much for the questions you've already asked, and happy to stick around longer to answer any more. Thanks so much.
Yeah, thanks a lot, Jesse. Yeah, I guess maybe if people want to leave, they can leave, and if they have some questions, they can ask some questions now. But thanks a lot, Jesse.
Yeah, thanks.
Okay, so I had one question. So if you go back to the Joule example,
The Joule example, yeah.
Yeah. So I think the thing that I wanted to ask was, does this way of thinking help you, for example, identify what sort of observable could distinguish models more easily, or something of that kind?
Yeah, so let me say a little bit more about this plot. So the standard way, so I apologize, I don't have backup slides about this. And if you want to talk about this, Jasmine Brewer is fantastic, and I'm sure you can get her to give a seminar about our work. And she's also working with me on some other things related to trying to disentangle quark and gluon jets in heavy ion collisions. But if I start off with a cross section for jets in lead-lead, that's shown in gray, and another cross section of jets for PP, the ordinary thing to do is to do RAA, where you take the ratio of the PP and the lead-lead curves, and you try to study jet modifications by taking this ratio. And what you can show is that that procedure is biased, and that you can draw the wrong conclusions from that, and that the jets, that is, you can have an RAA that looks like things are really modified, like an RAA of a half, even though the actual jets themselves are modified only like at the 5 to 10% level. And the reason why that's happening is that you have a steeply falling cross-section curve. And so tiny variations can actually give rise to large changes in RAA. So what we advocated for in this paper is this quantile matching procedure. And this quantile matching procedure, instead of saying, what's the ratio of the cross sections, it's saying, what's the ratio of the PTs? How much is the PT modified when I compare things horizontally? And that gives rise to these numbers here, which are much less extreme than you see in RAA. So like numbers like 0.8 or 0.9, whereas RAA would be like 0.4 or 0.5. And it also gives a mapping between the jet seen in one, in the lead-lead case. You can basically map it onto its nearest neighbor in proton-proton space, if you'd like. And you can kind of imagine that this proton-proton event was quenched to go down in PT. So what you're asking now is, you can ask, well, does this procedure give us better observables for thinking about how to gain access to this jet quenching phenomena? And the hope is that, this plot here turns out to be a certain limit of the sigma, of the cross-section mover's distance, where I actually suppress all substructure information, and I'm just looking at PT. And if you remember, there was a penalty cost in the energy mover's distance that's associated with jets that have different energy, and so that's basically what's being used here. And I'm not using any of the substructure. The hope is that if I use the substructure information as well, that will give me a more faithful map, and that more faithful map, I could check that by using Z plus jet data, and whether that map is more faithful. So I would say right now, we don't know how this can pick observables that does better, but we're hoping that we can. And if we succeed, then what you would say is, you would say, okay, this cross-section mover's distance is incredibly computationally expensive. And this is not the kind of thing that you actually want to run on whole data sets if you don't have to. Can we find a way of a proxy for this that's more computationally efficient, and maybe even one that's easier to compute using theoretical techniques, that nevertheless captures the same intuition that you would get from this procedure? So again, this is hard to do, and so you would prefer not to do it. Can you come up with observables that nevertheless map onto what you would obtain from this mapping procedure? So I think that's how I would anticipate this being used in the future.
Okay, but I guess the main point is that PT is more closely related to energy distance compared to RAA. That's your main point.
Yeah. Not only is it closer, I mean, in this case, it's exact.
Okay.
that ratios of PTs is literally what the cross-section mover distance does in the R goes to infinity limit. Essentially where you suppress all the substructure information. And that's extremely satisfying to me, because again, we didn't know about this logic when we wrote this paper, and now I can kind of say, oh, of course, this is why we thought about it this way. And now that I know that there's this mapping between these intuitions, now I'll just go directly to the energy mover's distance or the cross-section mover's distance. That's where I'm going to go first, and then come up with observables based on intuition developed in that space. So it seems to be a much faster way of getting kind of useful things out.
Okay, yeah, thanks.
Yeah, I had a question. I'm sorry if you talked about this. I missed a bit of your talk there. I wanted to ask you about the formal expression you have for the energy mover distance.
Yep.
Where you say you minimize over F. What exactly are the Fs here?
Good. Okay, so I didn't actually explain this. So let me try to explain a little bit more. Okay, so here is a blob of energy in one event in red, and here's a blob of energy in another event in blue. And I want to destroy all the red energy and transport it to blue. And I want to find the Fs that accomplish that. So if I only have two dots like this, it's easy. I basically transport as much of the red as I can to that blue dot, and then whatever's a deficit, I need to eat a cost associating with creating or destroying energy. So if there's just 2 points, this is trivial. But in this event here, I have many, many points, and I have to figure out, okay, for this red dot here, how much do I have to transport to this, to this, to this, to each of the blue dots? What's the cheapest way of rearranging all of the energy in order to get there? So there's many possible Fs. They satisfy constraints. So one of the constraints is that F has to be positive. Another constraint is that the F has to actually transport all of the energy from one to the other. And if I don't, I have to eat a cost. There's another probability conservation statement, which I'm forgetting, that this F has to satisfy. And then you search over all possible values of F that satisfy the constraints of actually transporting all the stuff from one to the other. And you try to find the one that minimizes this quantity. So you're minimizing over the set of all possible transportation plans of the F times the theta. So this is maybe easier to understand if I just go back to the one-dimensional example here. Okay, so if I'm trying to go from this blue blob to this red, and I want to transport all of this blue dirt to make this red dirt, clearly, well, one thing I could do is I could just take the dirt here and move it, this dirt here, and I could just move it right next door. So I could be lazy and just take this dirt here and just move it right next door. But then once I filled up this hole, then at the end of the process, I had to take this dirt way back here and I have to move it all the way over here, and that's expensive. So it turns out that the cheapest transportation plan in this one-dimensional example you can show is you take the dirt here, you move that one all the way to the end. The next pile, you move it as far to the end as possible, as far away as possible. You basically try to match the quantiles of one distribution, you match it to the other one. And so for one-dimensional optimal transport, matching quantiles turns out to be the best thing to do, which happens to be exactly what I was advocating for in this heavy ion study. So in the one-dimensional example, it's clear, but in the multidimensional case, this is a hard computational problem. And if you have M particles, roughly speaking, the computational cost to figuring out the optimal transport plan scales like M cubed log M. So for 100 particles, you're talking about something that scales, like 10 to the 6, and that can get really expensive. So this is a great conceptual idea, but it can be expensive to implement because finding those optimal Fs can be challenging. There are tricks for estimating it more quickly, and what's really cool is that the same challenge of trying to figure out these optimal transportation plans, this also is exactly what jet algorithms are trying to do. Jet algorithms are trying to summarize collections of particles and summarize them in a smaller number of jet objects, and the same computational challenges arise there. And what's remarkable is that the KT clustering algorithm is effectively a cheap way of trying to figure out the optimal transportation plan. And so KT clustering with so-called winner-take-all recombination schemes turn out to be a way of estimating optimal transportation plans between energy flows, which is kind of a cool fact.
Okay, thank you.
Did I answer your question?
I think it was a lot closer to answering the question. I think unless I look at an example of how exactly this is implemented, it will be kind of hard to understand. Right now, my mind is thinking a bit in terms of things like the salesman problem or some sort of optimization problem. But
that's exactly what it is. it's exactly what it is. Only this is one that can be done in polynomial runtime. So staring at this movie can be helpful just for getting some intuition. Okay, so when you watch this movie, you can see that some of these dots will end up like jumping in size, and that's because it turns out that one of the optimal things to do is to take a single energy deposit and splitting it up and actually sending it to different places. So that was done by this French mathematician I mentioned in the 1700s to more recent work is this idea that you can actually take deposits and kind of split them up, and that kind of notion of being able to split things up in the optimal way is one of the things that makes this rigorous in the mathematical literature. And you can see some other things in this movie. So this region of phase space here is empty, but as I transport, sorry, I have to wait till it cycles back around. So as I want to transport it to this green configuration, what you'll see is that I actually need to, oh shoot, this is the wrong video. Sorry. What I was hoping, I forgot this is a different video. What I was hoping is that you'll see that particles have to come into existence. That's because there's no transportation plan that can map the mismatch in total energy. But yeah, I mean, I think you're right that this is hard to figure out how you would actually do it. So this turns out to be an example of what's it called? A linear programming problem, and in particular one that is the algorithm that we use called the network simplex algorithm. And so if you actually look at the code that we're using and the optimal transport code, there are some kind of explanations about how this works. But roughly speaking, what you can kind of think of is trying to shuffle F's around, trying to test kind of almost like one particle at a time, like where should I move my energy to, and then keep kind of shuffling those things around like a kind of linear programming problem until I find the one that satisfies all the constraints and finds the minimum. But yeah, this is not something that's intuitive for people in particle physics, and yet it maps onto these things that are more intuitive that have appeared in the literature.
Okay, thanks. Yeah, that does help.
Yeah. And yeah, it's just staring at this movie of the transportation plan. Certainly, I learned a lot by just watching this thing in infinite repeat of what it ended up doing. Other questions?
I guess there are no further questions. So yeah, I guess that's it. So oh, I think Somain had a question. Oh no.
No.
Okay.
Fine.
Okay. Yeah. So then, thanks again, Jesse. It was a lovely talk, and hopefully you can come to TIFR sometime.
Yeah, thanks so much. Thanks for the invitation. And if anyone has other questions about this, I'm happy to communicate over email and send you more information. And I posted the link to the slides of my talk in the chat. And I think Rishi is recording this, so hopefully this will be available. And again, if something comes up, just let me know.
Okay. Yeah. That's good.
Okay.
I'll put download your talk and put it up on the webpage for our seminar series, if it's okay.
Great.
Okay. Great.
Perfect.
Okay.
Okay.
Thanks.
Thanks, everyone. Bye.
Bye.
Bye. Thanks.